Modern artificial intelligence is a multi-billion-dollar industry integrated into global software, but the architectural design that allowed these systems to scale traces back to a 2017 research paper authored by 8 researchers at Google. To understand why AI capabilities suddenly accelerated, we have to look at the specific processing bottleneck that this architecture was designed to eliminate. Before 2017, the most effective language models were recurrent neural networks, or RNNs. These systems process text as a linear sequence. They had to ingest a sentence by moving forward one word after another, carrying a growing memory of the sequence as they went. This created a linguistic problem. Meaning in language often depends on long-range dependencies, relationships between words separated by a lot of text. These older models often struggle to maintain a connection between a word at the end of a page and the subject introduced at the start. This also created a hardware problem. Because each step depended on the result of the previous one, the computation for the 10th word could not begin until the first 9 were completely finished. Modern GPUs are designed to perform thousands of calculations at the same time, but these models forced the hardware to wait. They were locked into a serial processing loop that couldn't fully utilize large-scale compute clusters. This meant that as datasets grew, training times became increasingly impractical. AI development was hit by a scaling wall where adding more hardware didn't result in significantly faster training. The researchers proposed a new architecture called the transformer. Their central idea was to remove recurrence entirely and look at all words in a sequence at once. They used a mechanism called self-attention. This allows the model to assign a mathematical weight to every other word in a sentence, determining which ones are most relevant to the word it's currently processing. When the model sees a word like bank, it checks the weights of other words like river or deposit. It resolves the meaning of the word based on the entire context of the sentence simultaneously, rather than waiting to reach the end of the line. By calculating these weights across the whole block of text, the system creates a direct map of how words relate to one another, regardless of the distance between them. Of course, language is complex. A model needs to track different types of relationships, like grammar, pronouns, and literal meanings, all at the same time. The transformer uses multiple attention heads, splitting the mechanism into parallel channels. One head tracks grammatical structure, while another maps pronoun references. This parallel mapping builds a multidimensional understanding of text in a single pass. The architecture effectively replaced the need for step-by-step memory with a system that computes an entire text block's internal relationships all at once. But removing the sequential order creates a problem. If the model looks at all words at once, it loses the ability to tell the difference between word orders that change a sentence's meaning. The researchers solved this with positional encoding. They added mathematical coordinates to the tokens, essentially stamping each word with its precise location in the sequence. This allowed the model to maintain the structural order of the language while still benefiting from the speed of parallel processing. While these concepts were elegant on paper, their real-world impact came from how they interacted with the physical reality of modern computing. Because the transformer could process an entire sequence simultaneously, it was significantly more parallelizable than older models. It allowed researchers to finally utilize the full power of massive GPU clusters. The results in the 2017 paper were stark. The transformer achieved a state-of-the-art 28.4 BLEU score in English to German translation, but it did so while training in only 3.5 days, a fraction of the time and cost required by previous top-tier systems. This provided the empirical proof that AI development could finally scale alongside hardware. Performance was no longer limited by the speed of a serial sequence. This architecture quickly moved beyond machine translation. It became a general-purpose blueprint for any system that needed to process sequences of information. By removing the sequential bottleneck, researchers were able to pre-train models on massive datasets like the entire public internet, leading to the development of increasingly large-scale systems. This scaling path led directly to the generative AI models that now power language assistants, automated coding tools, and modern search engines. By teaching machines to process relationships directly, rather than marching through data in a fixed line, this 2017 paper established the architectural foundation for the generative systems that now define the modern AI landscape.